Welcome, humanoids, to episode 6 in our course on the philosophy of climate change. As always, in my recording studio, it's Adam Briggle coming at you with the good Admiral Akbar. Let's jump into it. You might be wondering, who is this guy talking to me? Is that Adam? Yes, I shaved. No, I didn't lose a bet with Admiral Akbar. It's just really hot, and thought I'd put this up here because it's related to the class. Yesterday we were at 106. Average high for when I'm recording this here in August in Denton, Texas is 94. You could say it always gets hot in Texas. It's not unusual to go over 100, and that's true. Here we're getting to climate and weather, right? But it's also changing. This little graph on the right here, which comes from the National Science Foundation, shows you that we're experiencing much more record highs than we are record lows, and that has shifted over time. So that's showing you from like the 50s up to the 2000s, we're seeing greater number of record highs than we are record lows. And it all means that I had to finally get rid of that beard. That was too much. Okay. All right, yes, start with our Akbar approved tweet. I like this one. Plot idea: 97% of the world's scientists contrive an environmental crisis, but are exposed by a plucky band of billionaires and oil companies. Akbar liked that one, right? Oh yeah, he's loving it. Okay, but let's get into the serious stuff. Here are we. Okay, what are we gonna do? A bit on science as a body of knowledge, and then I'm gonna walk you through 10 climate basics. One note of caution and two implications about all of this. So again, we're in our climate science module. We're talking about climate science as a body of knowledge, just basic facts that are known. Next, we're going to move on to institutions and then methods and tools. So this is just a first pass into climate science. And it goes against my kind of inclinations to talk about science bracketed from the processes and the institutions and the people and the act of discovery that comes about to find it. But we're going to just take science as this corpus, this like bed body of knowledge sitting there. And we're going to talk more or less in the passive voice, what is known. Next lectures, we'll get to who is knowing it and how do they know it. But for now, let's just start with the basics. And I think it's important to do for a couple of reasons. Get to that in a second. Note, though, this is really challenging. I'm rifling through IPCC reports, and we'll get to the IPCC next time. Each chapter is hundreds of pages long, and I'm trying to say, well, what are the basics here? So it's humbling, and I think you could certainly challenge the things I come up with to some extent. At least in the sense of, you could say the list should be longer in terms of the basics. But I don't think anything I'm going to say today is controversial at all. Why is it important? A couple reasons to do this. It just gives us a foundation. Again, these are just facts that you need to know, I think, to have a kind of climate literacy. Also, and we'll get to this in a little bit here in some future lectures, there are forces out there, call it the carbon industrial complex, if you will, that would like to cast more doubt and create more confusion that's really warranted when it comes to climate change debate. We'll get to that, but knowing some of these basics at least provides you a check on when we're getting into some illegitimate or, let's just say, uncalled for questioning of basics that are established. Okay, so let's get into it. And I'm going to go fairly quickly through the first several of these basics because in a way, we've already touched on these, and there's really not too much more to say about them. So climate is long-term average weather, and we talked about how this is both real and a construct. A 30-year average climate, which is the kind of the graph I showed you from Denton. You know, what's the average high temperature in August, for example? That's a climate perspective for us, but of course, if you're looking from the Triassic period or something, it looks more like weather. So there is this kind of continuum in a way. I saw somebody put this, I liked it. It's like climate is your long-term batting average over several seasons of playing baseball, say. And weather is like how you perform on a particular game. Or climate is like your personality. And weather is like your mood of the moment. Those are maybe helpful metaphors. The Earth's climate system, I got a chart coming up, is super complex. And it's because it is a system, it's a set of processes that interrelate and interact with each other. The hydrosphere, the water, atmosphere, the air, lithosphere, the rocks, biosphere, the living things on the planet, the cryosphere, the ice, and of course the anthropo-human sphere, along with orbital variations and variations in solar radiation. All of that combines into the climate system. Climate change is significant and lasting change in the distribution of weather patterns. I mentioned, I think in an earlier lecture, there were palm trees once above the Arctic Circle where now there's ice, and now the ice is melting. Climate change can be change in average weather and or change in weather extremes. Okay, here's that little, what is this, info chart of simplified version of the climate system. And you can look at this, the slides will be up there. I won't spend a lot of time on this, but note just a couple of things. For example, the albedo effect. I don't think that word is on here, but when you look at atmosphere ice interaction, ice is white. It tends to reflect solar radiation. As the ice melts, it leads to darker ocean water, tends to absorb more solar radiation, which creates more heat, which melts more ice, which is what's known as a positive feedback loop. And we'll get to that later, but there's that going on. You've got vegetation interacting, trees growing, absorbing carbon, trees burning, releasing carbon, human activities, you name it. There's a lot of interactions going on to give us the climate system. Okay, let's keep going. We've already talked about the greenhouse effect and greenhouse gases, right? So this is an important feature of the climate system. We've also talked about, and remember that chart I showed you ticking by 100 million barrels of oil every day. I think we said that was something like 16,000 barrels a minute. That's a lot of greenhouse gases, primarily carbon dioxide, but also methane from our activities going into the atmosphere. As a result of this, we've increased the CO2 concentrations in the atmosphere. Okay, and that means that we're absorbing more heat. Here's another graph, this one from NASA. Again, I won't tarry on this too long. You can look at the slides and check this out, but energy, the reason I approach climate change as an energy issue is because energy is like this universal currency. You can think about just about any dynamic process going on planet Earth in terms of energy and conversions between different kinds of energy. So evapotranspiration, for example, like sweat, the planet is sweating, that's moving energy, cooling some parts and heating other parts. And so we have this energy budget or balance. You can see on here greenhouse gases and this back radiation, right? So turning heat energy back in on the planet. This is one of the key drivers now, or the key driver of anthropogenic climate change, but it's part of this bigger energy budget system going on. Okay, so by increasing greenhouse gases, we increase radiative forcing, raising global average temperatures. And this is known as global warming. Okay, which when I was a kid, that was really the term of art, global warming. Al Gore was talking about this. Climate change, though, is a better comprehensive term for anthropogenic, that is human-induced, human-caused impacts. And that's because different parts of the planet are warming at different rates. And there's all these complex interactions. Look at those two simplified graphs we looked at and imagine the complexity of a change in one part. So this extra back radiation, if that starts melting ice and the iced water dumps into the ocean, and if that affects ocean circulation patterns, well, then you might actually get regional cooling if something changes in that system, right? So I've got here, and this is where I'm going to need the Admiral. Are you with me? He's here. All right. How do I do this? I'm going to do new share, toggle over real quick to, this is a climate data scientist's Twitter feed. And you talk about differential warming. I hope you're seeing this. This is showing you 10-year averages on temperature on different latitudes, different parts of the planet here. And I want you to notice how the Arctic, northern regions of the planet are warming much more rapidly and dramatically than the Antarctic and southern regions of the planet. So it's just to show you, and I'll toggle back to my slides now, if you will help me, Admiral, that there's not uniform warming across the planet. And there may in fact be localized cooling depending on these interactions. So, and we're not just talking necessarily about heat, we're talking about precipitation and other weather events. So global climate change is probably the best term. Okay, Admiral, get me back to, where are we here? Here. Is that right? Okay. I hope you're seeing this. Okay. So last couple of ones. Anthropogenic human-caused climate change has current and projected impacts on Earth systems that are wide-ranging. Now we're starting to get into the complexities and the nuances of what is actually happening because of these basics that we know about, that we've covered. How is this affecting weather events, biodiversity, ocean acidification, sea level rise, species and disease distribution patterns? For example, are we seeing tropical diseases migrate northward as temperature and precipitation patterns change? That sort of thing. Now, these changes have and will in turn impact humans in many ways. Our food security, access to water, heat stress, infrastructure damage, diseases, migration, war, you can imagine other impacts. Okay, so that's my 10 climate basics. Let's get to one note of caution. Keep this headline in mind. This is recent from when I'm recording this, at least. We're having a big heat wave here in Texas and a big one in California, and the fires in California are going crazy. And it's not uncommon for people to say, here's climate change, right? Climate change is happening. But then the debate to quickly say, wait a second, we've always had fires and heat waves, so this isn't climate change. This is when it gets tricky, right? When are we warranted in attributing some change that we see to human-induced climate change? All right, so this is an IPCC little graph here. My note of caution, that measuring these impacts that we're talking about and attributing them to anthropogenic climate change is often difficult. It requires care in following evidence, characterizing uncertainties, and interpreting data. You don't want to slide, certainly on one hand, to just an all-out skepticism where you even call into question these basic facts. No, this is happening, right? We also don't want to slide into a sloppy, knee-jerk climate change, everything is climate change, without being attentive to the underlying dynamics and processes and what the science is actually telling us, insofar as it can tell us about these complex systems. This is from an article by Roger Pielke, who we'll talk about throughout this course a little bit, a climate scientist, climate policy scientist that I studied with, who has become somewhat controversial, but he uses IPCC data to say, actually, you know what, weather-related damages as a percent of GDP have actually declined in recent years. And there's a lot going on here. One of the things he notes is that we're actually not seeing an increase in frequency of cyclones or hurricanes. Get to that in a second. But one message is the world is getting wealthier, and the wealthier you get, the more resilient you get. And so even if there are, as there always are, extreme weather events, if you have more wealth, you can weather those storms, literally, better than you could in the past. Now, again, there's no guarantee that this trend, which is a good one, right? So weather-related losses as a percent of GDP going down, there's no guarantee that trend will continue, especially if current emission trends continue. But that is a trend, right? So and this is data he's getting from the IPCC, which is kind of the gold standard. Okay. Now, I won't read this whole thing. It's up on the slide. Last bit on this note of caution. This is kind of the way the IPCC talks, and we'll get into this. Well, it's likely that anthropogenic influences have led to warming of extreme daily minimum and maximum temperatures. There's medium confidence that this is affecting global precipitation. It's likely that we're seeing some extreme coastal high water due to anthropogenic climate change. But then note, they say it's too uncertain now, and we have a low confidence about tropical cyclone activity and its connection to anthropogenic climate change. So this is, I've taken you from the basics to now kind of the cutting edge of the way we're really talking about and trying to parse what can we say with what degree of confidence about the climate and the way we're impacting the climate. Okay, so that's my note of caution, that just knowing the basics is very important, but it's not going to be enough necessarily to make you be able to put these global statements about weather and climate down. We need to pay attention to the details when we get to that level. Okay, nonetheless though, there's two main implications I want you to leave with from this lecture and really from this course. This is maybe the biggest one. Scientists generally conclude that anthropogenic climate change poses risks to our collective future, and that aggressive adaptation and mitigation policies should be implemented. That one phrase is going to set so much of the rest of the course up and should stick in your mind. Yeah, there's a lot of complexity, but yeah, we know enough to act. But point two, okay, action. So this brings us into the realm of politics, where you have lots of values about human development, sustainability, progress, justice, right? Big ideals, ideals and values that are adjudicated in systems that are shaped inevitably by special interests, by power and money. So in short, getting from knowledge to action is tricky. And I'll leave you on one image I got from a TED Talk that I put in the notes if you want to follow it up for this lecture. It's almost like the scientists, the IPCC, what we're going to get to in our next lecture, this collections of thousands of scientists around the world, are the sentinels sitting up in the crow's nest on a ship. And they're saying, we're heading towards an iceberg, right? Now they're debating, like I showed you that little snippet in the previous slide, they're debating maybe how quickly we're going to hit that iceberg, what the damage would be specifically of doing that. But whether we're heading to troubles, point one here, is not really in debate. We are in trouble and we need to act. Okay, so that's the sentinel up in the crow's nest. But down on the deck, you've got all of these captains, major corporations, different nation states, even different local and regional governments. And they're all arguing with one another about, well, which way should we turn the ship? Even sometimes whether we should turn the ship or not, whether there's really an iceberg coming or not. So this is our predicament. That's a super simplified way to put it, and I'll probably challenge that later on, but it's a good way to start thinking about where we are as we get from the basics of climate science into the more nuanced cutting edge of climate science into what are we going to do in climate science politics. But that's enough for now. Those are our 10 basics, 1 note of caution and 2 implications, looking at climate science as a body of knowledge. Next time, let's look at the institutions that are doing this knowing. All right, until then, may the force be with you.